Continuing to talk about relative strengths of acids and bases and continuing to work with equilibrium constants for acids and bases, let's look at another situation. Acetic acid is the principal ingredient in vinegar. That's why it tastes the way it does. At equilibrium, a solution contains a 0.0787 molar of the unreacted acetic acid, and concentrations of the ions, the hydronium ion and the acetic acid ion, acetate ion, of 0.0018. What is the equilibrium constant, or Ka, for this acid? Well, the way that we would go about doing this is as follows. Let's minimize this. You know that the Ka is going to equal the concentration of hydronium ion times the concentration of the acetic acid ion divided by the concentration of the unreacted ion. This is going to equal, in this case, 0.0018 and times itself, so that's going to be squared, divided by 0.0787. And so that's going to equal 4.1112 times 10 to the minus 5. So the Ka here is 4.12 times 10 to the minus 5. Let's look at this second problem. Caffeine is a weak base. What is the value for Kb if a solution of equilibrium is the unreacted is 0.05, the reacted is 1 times 10 to the minus 3, and the hydroxide is 2.5 times 10 to the minus 3. Well, Kb is going to equal the ion, which is this caffeine, which is accepted a hydrogen ion, times, I'm not going to try to draw all that with this pencil, OH minus concentration divided by the caffeine concentration. This is going to be equal to 5 times 10 to the minus 3 times 2.5 times 10 to the minus 3 divided by 0.05. And this Kb is going to equal 2.5 times 10 to the minus 4. Now let's look at another problem here. It gives you the pH of a nitrous acid solution and asks for the Ka. So how do we go about doing that? Again, this is related to those problems we did this last week. You know that nitrous acid plus water gives the nitrous ion plus the hydronium ion. And the Ka, wait, let me write this in another place. Ka equals the hydronium ion concentration times the nitrous concentration divided by the nitrous acid concentration. Now if we start out and we know that the pH is 2.34, you take the pH and calculate the hydrogen ion concentration from that, or hydronium ion concentration. That's going to equal 4.6 times 10 to the minus 3. So you know that this is 4.6. Well, starting out, you have some concentration here. You have the concentration here of 0.0516. The concentration here is 0. The concentration here is 1 times 10 to the minus 7, but this is so much smaller than this number, we can essentially call this 0. This is going to lose x, this is going to gain x, and this is going to gain, and we know what this gains. And so this answer is going to be 4.6 times 10 to the minus 3. This is going to be 4.6 times 10 to the minus 3. And this is going to be 0.0516 minus 4.6 times 10 to the minus 3. And if we do all this, if we take the 0.5016 and subtract 4.6 10 to the minus 3, this becomes 0.047. So we have now 4.6 times 10 to the minus 3 squared over 0.047, and that's going to equal 4.5 times 10 to the minus 4. What is the concentration of hydronium ion and the pH in a 0.534 molar solution of formic acid? And here we have the equation and the Ka. This is a different approach to the same kind of problem. Again, we've done these kind of problems in the previous chapter, but let's take a look at how we would do this. We know that formic acid will react with water to give the hydronium ion. The reason they show an ant is the formic acid is what ants inject to sting their prey. And the Ka here is going to be the concentration of the hydronium ion times the concentration of the conjugate base for formic acid divided by the concentration of formic acid. And you remember with these, we know the concentration here is 0.534 when we start. We know that this is essentially 0, this is essentially 0. The change is going to be x for both of these. So at equilibrium, this is going to be 0.534 minus x. This is going to be x, and this is going to be x. So that 1.8 times 10 to the minus 4 is going to equal x squared over 0.534 minus x. Now, in this situation, because this number is so much smaller than this number, you can assume that this number is 0 for the purposes of doing this problem. This is only because when you subtract x from this number, it'll have a negligible effect on it. So that means that x squared is going to equal 1.8 times 10 to the minus 4 times 0.534. So that x is going to equal 9.8 times 10 to the 3 minus 3, excuse me. So the pH is going to be 2.01. Now here's another problem of the same type. It shows you in stepwise how to go about doing this. Determine the direction of change, determine x and the equilibrium concentrations, solve for x, and then check your math. Find the concentration of hydronium ion or hydroxide ion in a 0.25 molar solution of trimethylamine, a weak base. Here's the equation, and it gives you the Kb. This is exactly the same as this previous problem, and I am going to go ahead and do this, but it is exactly the same. You have trimethylamine, which is CH3, 3N plus H2O goes to form CH3NH. It's accepting a proton. That's why it's a base, times that. And we start out with a concentration here of 0.25, and we have nothing here and nothing here. The change is going to be X, and so you're going to end up with X here, and 0.25 minus X. And basically this X squared divided by 0.25 minus X is going to equal 7.5 times 10 to the minus 5. And again, you can assume that X is so small that it has negligible effect here. So that X squared is going to be 1.875 times 10 to the minus 5. X will be 0.33 times 10 to the minus 3. And the POH here is 2.36. And if I asked what the pH is, you would take 14 minus 2.36, and that would give you the pH of 11.64 would be the pH. Now here's a similar problem. Sodium bisulfate is used in some household cleansers because it contains an ion, weak acid. What is the pH of a 0.5 molar solution of HSO4? This is exactly the same as the last two, so I'm going to let you guys take a look at this one. And after you do it, if you have a question about your answer, just bring it to class and we'll do it in class. Now when you want to, if you need to guess, or you're trying to figure out if something is a weak acid or a weak base, sometimes you can use the periodic table to make your guess. You will notice the top row starts with CH4, then NH3, then H2O, then HF. You'll see that that's CNOF, which is the way they are in the periodic table, the second row. And you'll notice that methane is neither an acid or a base, ammonia is a weak base, water is neutral, and HF is a weak acid. And so as you go from left to right, the acid strength increases. Conversely, as you go from right to left, the base strength increases. Again, the second row, HCl, H2S, PH3, and SI4 shows you what happens. The acid strength decreases and the base strength increases. Also, as you go from top to bottom, the acid strength increases and the base strength decreases. So this is a new periodic trend that we haven't talked about before. Now, why in some respects does this occur? Well, let's take a look at this situation where you have two bonds, bond A, which holds the oxygen to the rest of the molecule, and bond B, which holds the hydrogen to the oxygen. Now, obviously, this is a hydroxide group. And the effect of how this is going to turn out all depends on the electronegativity and the effect of the element that's involved here labeled E. If the E has a low electronegativity, its attraction to electrons are low. There's a little tendency that exists for the central atom to form a strong covalent bond with oxygen, and bond A between the element and oxygen is more readily broken than bond B. If, on the other hand, that bond A is stronger than bond B, then the hydrogen is more likely to come off. And so if the hydrogen is more likely to come off, you have a proton donation, and this is an acid. If, on the other hand, the hydroxide is broken off, then you have a proton acceptance, ultimately, and this is a base. So also, another way to look at it is looking at the oxidation number for that central atom. As the oxidation number of the central atom, E, increases, the acidity increases. So, for example, at the bottom, you have sulfurous acid. The oxidation number of sulfur there is +4. Sulfuric acid, the oxidation number is +6. Sulfuric acid is a stronger acid than sulfurous acid. Nitrous acid, the nitrogen is +3. Nitric acid, the nitrogen is +5. Again, the higher oxidation number is the stronger acid.